All right, welcome. So to continue from where we stopped in the previous video, we did a derivation on capillarity. So we're basically going to apply the formulas we have there to solving this problem. So let's say we have this problem which says when a capillary tube is dipped into a vessel of water, the water rises by 5.75 millimeter beyond the surface of the water in the vessel. The same tube is dipped into a vessel of mercury. If the variation in the level of mercury is 0.2 centimeter, question says calculate the surface tension of the mercury. Assume the surface tension of water to be 75 by 10 to the power of minus 4 newtons per meter. Angle of contact of mercury to glass interface is 130 degrees. Densities of water and mercury to be 10 to the power of 3 kilograms per meter cube and 13.6 by 10 to the power of 3 kilograms per meter cube. They say take gravity to be 9.81 meter per second squared. Okay, so what we'll do now is simply let us bring out the parameters for water first. Okay, let's get the parameters that was given for water. First of all, we have the vessel, okay, containing water. So we'll have a vessel containing water, and condition says that a capillary tube was dipped into this vessel and the height of water increased inside the capillary tube. So the height of water was given to us as 5.75 millimeter. So of course we are going to convert this height to meters. So let's simply put that down here. Height of water H equals 5.75 millimeter. So we simply convert this to meter. To convert this to meter, it's either you divide by 1000 or you simply multiply by 10 to the power of minus 3. It still gives you the same value. Okay, so simply height of water is simply equal to 5.75 by 10 to the power of minus 3 in meters. Okay. We were also given the density of water. We were also given the surface tension of water to be 75 by 10 to the power of minus 4. So surface tension coefficient for water, let's put that down here. Surface tension, okay, coefficient, okay, for water, simply gamma W was given as 75 by 10 to the power of minus 4 newtons per meter. That was given to us. And density of water was also given as 1000 kilograms, 1000 to the power of, sorry, 10 to the power of 3 kilogram per meter cube. So we have rho of water equals 10 to the power of 3 kilograms per meter cube. All right, so now the condition says this same tube is dipped into a mercury containing, okay, this same tube is dipped into a container or a vessel containing mercury. First of all, what is the variation in height for water? Variation in height for water from the formula is simply given as what? 2 times the surface tension coefficient of water all over the radius of the tube times the gravity times density of water, okay? Times density of water. So from this condition, we are given the height of the water in the tube. We are also given the surface tension coefficient of water in the tube. Okay, we were also given gravity, of course, is constant, and then density of water was given to us. The only thing we weren't given in this equation is simply what? The radius. So if the depth or if the same tube is dipped into a container or a vessel containing mercury, it means that same tube has the same radius. It means the radius of the tube doesn't change because it's still the same tube here that I removed from the water and dipped into a container or a vessel containing mercury. So the radius of the tubes remain the same. So all we need to do is simply what? Look for the radius of the tube. Using this condition for water, look for the radius of the tube. That's all we need to do. Okay, so if we do that, we are going to obtain that. So if we make radius subject of the formula from here, we are simply going to obtain that the radius of the tube, okay, radius of tube, which is simply R, is simply equal to 2 times surface tension coefficient of water all over um, density of water, gravity times the height of water in the tube. This simply gives us the value for the radius of the tube. Okay, so radius is now equal to 2 multiplied by the surface tension coefficient of water was given to us as 75 by 10 to the power of minus 4. So put that down, 75 by 10 to the power of minus 4 all over density of water is given as 10 to the power of 3 multiplied by, okay, it was given here 10 to the power of 3 multiplied by gravity. Gravity is constant, 9.81, okay, multiplied by the height of water, and the height of water was given as 5.7 by 10 to the power of minus 3. So we simply have 5 times 75 by 10 to the power of minus 3. So this simply implies that the radius of the tube is equal to 2 times 75 times 10 to the power of minus 4, 0.015 all over 10 to the power of 3 multiplies 9.81 multiplies 5 by, so this is 5.75, okay, multiply 5.75 by 10 to the power of minus 3, 56.4075. So this simply implies that the radius of the tube r is simply equal to, so radius gives us 2.67 in meter. So this becomes the radius of the tube. Now this same tube is dipped in a mercury, a vessel containing mercury. So we have a vessel which contains mercury now, and this same tube having the same radius is now dipped into this mercury. Of course, there is going to be what, a drop in the height of mercury. There is going to be a drop in the height of mercury because mercury has a very strong cohesive force between them, between their molecules. So their cohesive force is very strong, so they tend to cling to one another, to themselves, whenever they are dipped in what, in a glass. So there's a drop in the height, and that height was given to us. The height of mercury from the question was given as h equals 0.2 centimeter, if I'm correct. Okay, yeah, 0.2 centimeter. So the height of mercury was simply given as 0.2 centimeter, and of course the contact angle was also given, the angle of contact between the tube and the surface of the curve meniscus formed by the mercury. This angle was given as 130 degrees. Okay, now let's bring out the parameters for mercury now. The height of mercury is simply 0.2 centimeter, and we also have to convert 0.2 to meters. Converting 0.2 to meters simply means dividing it by 100. So this is simply 0.2 all over 100. So which means the height of mercury in the tube is simply equal to, simply 2 by 10 to the power of minus 3 in meters. This simply gives us the height of mercury in the tube. Also, we were given the angle of contact. Theta was given to us as 130 degrees. Okay, that's theta. The angle of contact between the mercury to glass interface, or mercury to glass interface, was given as that. Okay, that was given. The density of mercury was also given. Density of mercury was also given as 13.6 by 10 to the power of 3 kilograms per meter cube. So these are all the parameters I was given for mercury, and the question says we should find the surface tension of mercury, simply unknown. Okay, so I simply said if this same tube is dipped into the mercury or the vessel containing mercury, it simply means that the radius of the tube does not change. The tube is the same, so which means its radius is also what, the same. All right, so the variation in height for mercury is simply given as 2 times the coefficient of surface tension for mercury all over the radius of the glass or the tube times gravity times density of mercury multiplied by cosine of the angle of contact. Now notice that in the first case when we did for water, there was no angle of contact. That value is 0. So even if you had added 0 here, cos 0 will still give you 1. That's why we use the normal equation. But in this case now, we have an angle of contact. So you must always introduce the cosine of that angle. Okay, so we know the height of mercury. We know the radius of the tube. We know gravity. We know density of mercury. This is what we're looking for now, the coefficient of surface tension in mercury. So simply make this subject of the formula. Coefficient of surface tension in mercury simply becomes the radius times gravity times density of mercury multiplied by the height of mercury in the tube all over 2 cos theta. So we simply have this. So this simply means that okay, coefficient of surface tension in mercury is now equal to the radius is given as 2.67 multiplied by gravity is constant 9.81 multiplied by density of mercury was given as 13.6 by 10 to the power of minus power of 3 times the height of mercury was given as 2 by 10 to the power of minus 3 all over 2 cos. The angle of contact for this was given as 130. So you simply have this, okay? So the surface tension coefficient for mercury is now equal to, give me this value again, 712.4414, okay, all over, please give me 2 cos 130 minus minus 1.2855, okay, 56. All right, so we simply have this. Now the negative sign actually shows the depression in height of mercury in this in the tube. That's what the negative sign shows. Okay, that's the reason why we're having a negative value here. It actually shows depression of height in the tube. Okay, all right, so we can simply obtain that the surface tension coefficient for mercury is simply equal to 712.441 for divides 1.2856. So we have minus 554.17, okay, in newtons per meter. Once again, like I said, the negative sign only shows that there is a level or a drop in height in the height of mercury. So we have to actually exclude negative sign because surface tension can never be negative, but negative sign only shows the drop in height in the level of mercury inside the capillary tube. So we can simply write that the surface tension for mercury is simply equal to 554.17 newtons per meter. So that becomes the answer to that problem. All right, guys. So I hope you find this video very interesting and helpful. Please, if you do, don't forget to share your thoughts in the comment section. And of course, if you're new to the channel, please hit the subscribe button to keep getting updates on content such as this. I will see you in the next video. Thanks.